I will begin with a word of prayer. So, here we go. Dear Father, we thank you for this day, and I thank you for this class. I just ask that you'd be glorified at what we do, and that we'd understand a little bit more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right, I see I have forgotten my markers, so hopefully these will work for a second. So last time we defined the Laplace transform of f, right, to be the integral from 0 to infinity of e to the minus st times f of t dt, right? And we learned that the Laplace transform is linear, and then we calculated a few things, right? Like for one thing, we saw that the derivative with respect to t of the, with respect to the partial derivative with respect to s of the Laplace transform of f, right, was equal to minus the Laplace transform of t times f, right? That's one thing we did. We figured out the Laplace transform of t times the function is actually the partial derivative of the function. On the flip side, we saw that the Laplace transform of df dt, although we used y, was equal to s times the Laplace transform of f minus f of 0, right? So if I write this in a slightly different notation, it's like this, right? We got like partial big Y, partial S is equal to, minus the Laplace transform of t times little y, right? But on the flip side, the Laplace transform of dy dt is equal to s times big Y minus little y of 0. Notice what's going on here is that differentiation in the s domain is causing a multiplication by t in the t domain, and likewise differentiating in the t domain suggests we have a multiplication by s in the s domain. So there's some sort of like duality between differentiation and multiplication in these two different worlds, the world of t and the world of s, which is kind of neat. Of course, this is like the major one because this allows us to trade a differential equation for an algebraic equation like we saw last time. Finally, let's remind ourselves what we already worked out. We've worked out that the Laplace transform of 1 is 1 over s. The Laplace transform of, let's see here, e to the at, 1 over s minus a. The Laplace transform of e to the alpha t cosine beta t of s, and the Laplace transform of e to the alpha t sine beta t of s was equal to, let's see here, we had s minus alpha divided by s minus alpha squared plus beta squared, and of course here beta divided by s minus alpha squared plus beta squared. What was the other thing we learned? We also learned that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. And there was one other thing we learned, which was, well, at least one other thing. Oh yeah, I guess that's it right here, This business right here. Trying to think anything else. We talked a little bit about inverse Laplace transform. We said the inverse Laplace transform is, linear. So let's just write down some basic inverse Laplace transform here. What's the inverse Laplace transform of 1 over s? What's the inverse Laplace transform of 1 over s to the n? What's the inverse Laplace transform of, say, 1 over s minus a? what's the inverse Laplace transform of, s minus alpha over s minus alpha squared plus beta squared? What's the inverse Laplace transform of beta divided by s minus alpha squared plus beta squared? All right, so we just have to work backwards, right? Work backwards. The inverse Laplace transform of 1 over s is 1. The inverse Laplace transform. So this one here, let's take this equation here, and this tells us what? That the Laplace transform of 1 over n factorial, right, times t to the n is equal to 1 over s to the n plus 1. See that? So if I'm taking the Laplace transform of 1 over s to the inverse Laplace transform of 1 over s to the n, what I want to do there is do t to the n minus 1 divided by n minus 1 factorial. Notice that that works. In the n equals 1 case, we've got t to the 0, which is 1, right, divided by 0 factorial, which is 1. So that these are consistent. This is e to the at, right? This is e to the alpha t, what? This one's a cosine beta t, and this one's a sine beta t. I guess there's one other thing that we might commonly need to work on, recognizing the inverse Laplace transform of 1 over s minus a to the power n. What's that going to be equal to? Remember, we have a shift theorem. That's the one thing I haven't written up here yet, I guess, is like the Laplace transform of e to the at times f is equal to the Laplace transform of f at s minus a. This is the shift theorem. So if I put that into practice here, this also means that the inverse Laplace transform, let's say of f of s minus a, is equal to e to the, of t, would be equal to e to the at times f of t, where big F is the Laplace transform. All right, so like here, this is what? We just do what we do. Yeah, e to the at, very good. Mm-hmm.
Or to the t to the n.
All right. So these are handy to know. All right. So that's just a quick recap of the things that we did last class. But what I need to talk to you guys more about today is how do we take the inverse Laplace transform of different things. So let's see here, example 1. Consider f of s equals to, let us say, s plus 3 over s cubed minus, let's say, 16s. Find the inverse Laplace transform of f. Can we do it? What should we do? Man, these markers are not good. I need to go back to the department and get some better markers, guys. I'm sorry. Maybe these work, I don't know. So, if you're first of all, we can't just take the inverse Laplace transform of this because it's none of our basic inverse transforms, right? So, what we're going to do is we're going to use partial fractions. Ooh, this one works. Yay! Partial fractions decomposition to convert it into basic like basic algebraic functions. So this is s times s squared minus 16, right? So the first order of business, guys, is to factor the denominator. And so here that is s times s plus 4 times s minus 4. I spoke too soon. This marker's also trash. What's that? No, I just need to walk back to my office. There's a bag of them there. So we'd like to find A and B and C to make this equation hold true. All right? So this is one problem we'd like to solve. You guys got it? Example 2, we'd like to calculate if f of s is equal to, let us say, 3s plus 7 divided by s squared plus 6s plus, let's say, 13. Find the inverse Laplace transform of this one, all right? So you guys, I will let you work on these for a minute. I'm going to go get some markers, and I'll be back. All right? See if you can solve them before I get back. Unnecessary but fun. Let's see here. Did you guys get them? All done? All solved? End of class? Where are we at? No? The first one, I think, is not too bad in terms of like, this should be similar to a calculation that you did in Calculus 2, right? For the partial fractions decomposition, integrate rational functions, right? So we do multiply by the denominator. If I do that, I get s plus 3 is a times s plus 4 times s minus 4 plus bs times s minus 4 plus cs times s plus 4. So there's a lot of cancellation that goes on there, right? And then this time, this is easier than the one I did last class. Last class was annoying because it had a repeated root, which made my life, you know, a little bit difficult in that we had to plug in kind of random ad hoc numbers. Here we'll just plug in the roots, and the a and the b and the c will just pop out at us. Easy, easy, easy. So s equals to 0 gives us 3 is equal to minus 16a. Gone, gone. Therefore, a is minus 3/16. S equals to 4. We get 7. 0, 0, 4 times 4 plus 4. 4 plus 4 is 8, so I get 32c. Therefore, c is apparently 7 over 32. And then we can plug in s equals to minus 4. That gives us minus 1. That's 0, that's 0. Only the middle one survives. We get a minus 4 times a minus 8, which is, I think, 32. So therefore, b is minus 1 over 32. So this means when we calculate the inverse Laplace transform of f of s, we can do this rather nicely. We can say, oh, okay, well that's minus 3/16 times the inverse Laplace transform of the 1 over s, right? Minus 1 over 32, inverse Laplace transform of the 1 over s plus 4, plus 7 over 32, inverse Laplace transform of 1 over s minus 4. I pulled the constants out because why not? Now you might notice something here. Question. I mean, I'm being unequal in my notation in some sense, right? I wrote the of t over here. You know, I'm being a little bit sloppy by not writing of t, of t, of t here. Perhaps I should. I just wanted to do that to say that I wouldn't typically take off points for you guys if you didn't. And you might say, well, does that even matter? And the answer is yes, it does matter for the thing we'll talk about towards the end of class. Oh, man. So sad. But anyway, here we go. So what we got is minus 3/16, minus 1/32, e to the minus 4t, plus 7/32, e to the 4t, and there you go. That is the inverse Laplace transform of that function. Any questions about this? I mean, is the method clear enough? Like we have to rewrite the expression we're given as a sum of things we know the inverse transform of. What do we know the inverse transform of? Just the things over here. So we have to break it down to these basic pieces in order to take the inverse transform. So if you look at example 2, again, we look at the sideboard. It's not there, right? It's not there, right? So first of all, the question is, does this factor or does it not factor, right? So like my example 3, will be, f of s equals to 2s plus 1 over s squared plus 3s minus 4, all right? And see, that problem's going to work out different than example 2. Example 2 and example 3 are very different examples. And the reason for that is that the structure of the denominator is completely different. One of those quadratics factors, one of them does not over the reals. Which one is which? Yeah, example 2 is non-real. Example 3, we can just factor that thing, all right? So the way we approach these problems is pretty different. This one, I will show you a trick, all right? So we don't even need to do any kind of we don't need to do the partial fractions thing for this one. We just need to be creative. So here's the creative. So first of all, we complete the square in the denominator. All right? Plus 4. Because this squared out gives me a 9. 9 plus 4 is 13. Now, we could also begin example 3 in the same fashion. That would be silly, but you could. See, this is s plus 3 halves squared minus 9 fourths minus 4, right? That would be completing the square there, which I wouldn't recommend because there's something much more obvious, right? This is what? I got it, yeah, an s minus 4, s plus 1, right? So when we come back to this example, we're going to do a over s minus 4 plus b over s plus 1. We're going to use partial fractions decomposition. So what I've written below there, guys, is just for those of you who are still getting used to completing the square. This is just a parenthetical comment, by the way. Okay, like you don't have to do that. I'm just showing you completing the square will always factor a quadratic. The next step is like, this is minus 25 over 4. So you end up with like 3 halves plus 5 halves or 3 halves minus 5 halves, which respectively is, like the 4 and the minus 1 over there. Anyway, who cares about that? So we have this s plus 3 over here. Let me get back to this one. We want to create that s plus 3 in the numerator. We need that because, remember, the inverse Laplace transform of the cosine piece requires an s minus alpha upstairs. All right? So start with that piece. I've got a 3 here. I can't get rid of that. So I've got this 3, and I just put s plus 3. All right? You're like, well, there's not an s plus 3 there. That's right. There's not an s plus 3 there. So to be fair, I must subtract the thing I just added, namely 3 times 3. See? Now that's exactly equal to this, right? This 3s is equal to these terms. And I'll leave the 7. I'll just leave it. All right? Next step, this is 3 times s plus 3 over s plus 3 squared plus 4, big brackets. And let's see here. I got a, oh, that's funny. So I got a minus. This is, aw, man. All right, permission to take the 7 and make it into a 17. This is too easy for us. It's too easy. We're making that 7 into a 17. There we go. My apologies for this hideous Carolina blue. 17 minus 9 is 8. So I'll put an 8 out here. And we got ourselves What would you say? Did I do the arithmetic wrong? It's possible. In order to calculate the inverse transform, it's a very particular pattern. I need the beta upstairs. I need a 2 in the numerator to make the thing in brackets with the blue line here the right pattern for sine. But there's no 2, right? So the one way you could do, of course, so in order to multiply by 2, I simply divide by 2.
Why is it minus?
The minus is because, oh, I forgot. Plus, thank you. Sorry. Yeah, 17 minus 9 is not negative 8, it's plus 8. Thank you. Of course, you could be a human and instead write this as simply 4 times 2. That would also be fine. I'm trying to illustrate the arithmetic idea here, which is just pull out whatever number you have, put the 2 you want here, and then divide by 2. That's multiplication by 1. You can always do that. You know? I'll do another example in a minute. But so anyway, lo and behold, we have that the inverse Laplace transform of f at time t is equal to 3 e to the minus 3t cosine 2t plus 4 times e to the minus 3t sine 2t. There you go. That is immediately clear from that. Working again with the sideboard. Do you guys follow me? So it's a very particular algebra. It's an algebra which is aiming to go to the results we already know. Very particular patterns, right? We need that 2 here. We need that s plus 3 there, all right?
So you're kind of just trying to make it into
Yeah, it's a lot like integration, right? Like where we're trying to make the expression fit a certain pattern we already know the integral of. So if we have something that doesn't fit an integral we know, we try to make a substitution to turn it into something that has a known antiderivative. This is basically the game we play here. Now here, multiply by the denominator, we've got 2s plus 1 is equal to a times s plus 1 plus b times s minus 4. And then if we plug in, yeah, s equals to minus 1, we get minus 5b. If we plug in s equals to 4, we get 9. It's 5a, I think. So b is 1/5. A is 9/5. And as such, f of s is 1 over 5 times s minus 4. My apology that my 5 and s look so much alike. It is what it is. I'm sorry. I can't fix it. And that was supposed to be a 9, so there you go. And then plus 1 over 5 s plus 1. All right. I try to avoid problems with 5s, but it just happens, you know. So then the inverse Laplace transform of f at time t is simply 9/5 e to the 4t plus 1/5 e to the minus t. Both of these, I've simply used the fact that the inverse Laplace transform of 1 over s minus a is equal to e to the at, right? A equals to 4, and also a equals to minus 1. Is good? Yes, no?
In the original denominator factor, it should have s plus 4 and s minus 1.
Oh, man. How can I fix that? It's good?
Problem solved.
Does that fix it? That might fix it. Ah. There you go. Sorry about that. Yes, thank you. I would please make this comment 3 minutes ago. But it's okay. I do appreciate the comment. It's better than not having it, for sure. Or having it after class, as is my son's custom this semester. Son is evil. All right, here's another one. Suppose we had f of s equal to, I don't know, 7s over s squared minus 12s plus 47. There, that's weird enough. Let's find the inverse Laplace transform of this thing. All right. So here's the deal. This is 7 s factors. Well, it doesn't factor, right? So we've got s minus 6 quantity squared, right? And that adds a 36. I have to take 36 away. 47 minus 36 is 11. Plus 11. If we complete the square and we got a plus, that means it is irreducible. It's a prime polynomial. It cannot be factored over the reals. We are on a collision course to an inverse transform which must land on sines and cosines times exponentials, right? If it does factor, the inverse transform goes to a sum of exponentials, real exponentials. All right? Okay, so then, with that in mind, we'll do s minus 6 here, right? But to be fair, I just subtracted 42, so I must add a 42, right? So therefore, the inverse Laplace transform of f is 7 e to the 6t times the cosine of the square root of 11 times t, right? And so let me just do a little math right here. I don't want a 42 there, right? What do I want? See, I know that the inverse Laplace transform of the square root of 11 divided by, s minus 6 squared plus the square root of 11 squared, this, by our work last class, is exactly e to the 6t sine to the square root of 11 times t. But I don't have a square root of 11 there, right? So how do I make it appear? Magic? Yes. Magic like this. Square root of 11 divided by the square root of 11. See? Now it's there. And as such, that gives me 42 divided by the square root of 11 e to the 6t sine of the square root of 11 times t. All right? So at this point, I think I've shown you my main calculational tricks for basic inverse Laplace transforms. There's, of course, always more. Here's one. If we had f of s equal to, say, s plus 2 over s squared plus 6s plus 9. What have I done? Let's see here. So complete the square in the denominator. And, oh, that happened. Okay. Now, there's nothing quite like that. So here, this is yet another trick. I like for this one, I can do s plus 3 minus 1, right? Which is going to give me s plus 3 over s plus 3 squared minus 1 over s plus 3 squared, also known as 1 over s plus 3 minus 1 over s plus 3 squared. This is a little trick, yeah? What's the other way to do this? Partial fractions, right? You look at the partial fractions decomposition, you assume you have a over s plus 3 squared plus b over s plus 3. I forgot to move the camera about 5 minutes ago. So much sadness. Sorry if you didn't come to class, but on the other hand, you didn't come to class. Let's see here. Where was I? So like the other way to do this is instead of doing my trick, when you get to this, you go, okay, well, this is equal to like, a over s plus 3 plus b over s plus 3 squared. And then algebra, you get a is equal to apparently 1, and b is equal to, well, apparently minus 1, right? But I don't have to do that algebra, because I can do the blue algebra, which is easier, in my opinion. Adding 0 is easier. So anyway, once we have that, what's the inverse Laplace transform of f of s? Well, we've got inverse Laplace transform of 1 over s plus 3. That's easy. We talked about that already. Minus the inverse Laplace transform of 1 over s plus 3 quantity squared. A little bit less familiar. We haven't done that. But what we got here is simply this: e to the minus 3t minus t e to the minus 3t. Because if we have s plus 3 squared, that inverse Laplace transforms to t e to the minus 3t. We good? I mean, there's more to learn, of course, but I think it's a good start. Now, at this point, I'm going to transition and turn to talk about something that is, I would say, more challenging than what we're currently doing. Maybe that's wrong. Maybe it's not more challenging, but it's certainly weirder. It's also the strength of the method, all right? The whole reason we're doing Laplace transforms, ultimately, is that it allows us to solve discontinuous functions. Like we have a forcing, if you have a, okay, so for example, if you've got, a switch in an electrical circuit and turns things on and off, right? What's the mathematics of that? Like, how do you model something that has sort of it jumps on and off, that kind of thing, right? What's the mathematics of that? And so to understand that, we need to introduce some new notation. And this new notation will free us from the burden of writing case-wise defined functions. We're going to find a way to take a case-wise defined function and wrap it into a linear combination of what are called unit step functions. Or these are also known as Heaviside functions in honor of, I think, Oliver Heaviside, who popularized some of this stuff, I guess. I don't really know all the history. But so first order of business, I need to tell you about the unit step function. So this is a definition. U of t, we're going to let this be 1 if t is greater than 0, and we're going to let it be 0 if t is less than 0. And actually, I don't know really what u of 0 should be. I don't really care. Okay, so I don't want to commit to it. It doesn't matter. Ultimately, we're doing integrals, and integrals don't care about a point if your function's finite. You'd be like, wait a minute, you mean a function couldn't be finite? And we could integrate it? I did say that. In about a week, we'll do that. So this is the unit step function. The graph of it, likewise, if we did, u of, say, t minus a, how would this work? This would be 1 if t is greater than a, and it'd be 0 if t is less than a, right? And I also like to talk about, and this is not, I don't think this is in your book at all, but the gate function from a to b of t. What this is going to be is it's 0 if t is less than a. It's 1 if a is less than t is less than b. And it's 0 if t is greater than b. And again, my apologies, I'm not committing to what it is at a and b. You could make it 0 or 1, it doesn't really matter. Here I am assuming, though, I am presupposing that a is less than b. All right. Okay, so check this out. G AB, I can write as u of t minus a. All right, let's think about how that works graphically. Here's a, here's b, right? So u of t minus a, it turns on at a and it just keeps going like that, right? This g, I want it to just be 1. Let me kind of sketch. I'm gonna like hatch where the graph is above the. I'm gonna color in under the graph so you can see it. It's kind of hard to see otherwise. But it's just a bump, right? Like the gate function. It's 1 from a to b, and it's 0 otherwise. So this unit step function, the red one, it kind of does part of it, but what do we want to do what? Past this point, we want to get rid of it, right? So what can we do? How about this? We subtract the unit step function of t minus b. See, if I do that, notice like the step function, like this would be u of t minus b, right? And if we subtract these two, they cancel out past here, right? So the blue one is 0 over here like that, right? The red one is 0 over here like that. So if you take the difference of the red and the blue, you get 0 before a, you get 1 between a and b, and you get 0 afterwards. This is a way to turn a function on from a to b and then turn it off, all right? So let me show you how we can use this gate function to assemble case-wise defined functions using this sort of technology. Example 6. So if I have f of t, let's say t squared, 0 less than t, less than, let's say, pi, and then I have cosine t for t for pi less than t less than 10, and then I have e to the t for t greater than 10. I can rewrite this case-wise defined function. I'm going to start giving quizzes at the end of class. Let's see here. We can write this case-wise defined function in terms of gate functions, right? I do think attendance has gotten a little bit kind of sketchy in my courses lately. I'm going to have to go to like some sort of like quiz every day kind of thing next semester or something. I don't know. Or maybe I just won't. It's a lot of work. So what I do is simply this. T squared times the gate function from 0 to pi plus cosine t, the gate function from pi to 10. And then plus e to the t times the unit step function at 10. See, because that just turns e to the t on at time 10 and just leaves it on forever, right? Think about how that works.
It's like logic.
It is like logic, yeah. These are essentially mathematical functions to implement logical operations, yeah. Yeah, in fact, you can build circuits that correspond to logical operations. In fact, oh yeah, these are computers. Yeah, that's what it is. But so this, we can do more. we can rewrite this in terms of unit step functions, okay? So this is actually like t squared times u of t, yeah, u of t minus pi, right? Plus, I'll write it in 3 lines, cosine t times, big brackets here, cosine of, oh good grief, u of t minus pi minus u of t minus 10, right? And then plus e to the t times u of t minus 10. Now, for things I'm about to show you, reasons, we would like to put all of the terms that have the same unit step function together, because like the next thing we're going to do is take the Laplace transform of these things, all right? So it's better for us to write this as like t squared times u of t plus brackets cosine t minus t squared u of t minus pi. So if I was an engineering professor and I got to the point of not caring about anything, I would just go straight to what I'm writing and say, figure it out. Something like that. Or if I was a math professor, I didn't care. But I still care, so I'm still showing you how we can logically understand getting from here to here. I understand it in terms of the gate functions. Now, do you have to show these steps? No. Like once you understand what we're doing, you can go straight from here to here. It's not illogical, but you need to understand what you're doing, all right? So we can do this for any case-wise defined function. We can convert to a linear combination of the case functions multiplied by Heaviside functions, multiplied by unit step functions, all right? An example constitutes proof, right? I mean, yeah? No? That's how you learn? Ah. There is something more ambiguous there than you might realize in terms of like what's the correct proof. It is dependent on your audience. You know? Like if you don't convince anybody, is it a good proof? I don't know. It might be. You might just be the most smart person on earth and you can't convince anybody of your true thing. Have you really proved it? You know? If a tree proves in the forest and no one's there to hear it, does it make a sound? I don't know. Maybe. Stupid comments aside, let us calculate what is the Laplace transform of, let us say, f of t times u of t minus a. How's this going to go? Well, we start out with the integral from 0 to infinity of e to the minus st f of t times the unit step function of t minus a dt. All I've written so far is merely the definition of the Laplace transform acting on a function times the unit step function, yeah? So, can we do this? This integral is really, really easy to do from time 0 all the way up to time a, right? What happens from time 0 to time a? U of t minus a is what? It's 0, right? So the integral is straight up 0 all the way up to a. So we can rewrite this as integral from a to infinity of e to the minus st f of t. And then what's u of t minus a past a? Well, it's just 1, right? So I could put the 1 here, but I just won't. Right? That's just common sense and the definition of the unit step function. Now, if you look at this, it's like, it's not quite right, right? So, see, because we need the integration to go from 0 to infinity for it to be a Laplace transform, right? So if I want to rewrite this as the integral from 0 to infinity, right, of something, I need to make some sort of like u substitution. U equals to t plus what? Or t what? What's the substitution we want to make? U equal to what? How can I make t equals to a becomes u equals to 0? What's that? No. I want t equals to a to become u equals to 0. T negative a? Yeah, t minus a, right? If I do that, then if I put t equals to a, I get u equal to 0, right? And this is also very nice in that, well, du is equal to dt, right? What's t equals to in this world? U plus a, right? So I have e to the minus s. T is u plus a, right? Making a substitution here. F of, well, t is u plus a. My dt was du, right? Now, an algebra step. This is actually e to the minus sa, integral from 0 to infinity of e to the minus su times f of u plus a du, right? But you should recognize that u is just a dummy variable of integration, right? So I could just as well change the u to a t, or I could just recognize what this is. This is e to the minus sa times the Laplace transform of f of, well, we probably could say t plus a. That might be more understandable, I suppose, of s. So if you want, I can put another step in here if that's confusing. Here's my extra step, e to the minus sa integral from 0 to infinity of e to the minus st f of t plus a dt, you know, u equals to t substitution. I'm unsubstituting, if you like. So that's what happens with a unit step function. So for example, if we were calculating the Laplace transform of e to the t times u of, let's say, I don't know, t minus 3, well, that's equal to what? That's equal to e to the minus 3s, I think, right? E to the minus 3s times the Laplace transform of what? F of t plus a, right? Here a is equal to what? A is 3, right? My f of t is what? E to the t, right? So what is f of t plus 3? F of t plus 3 is e to the t plus 3. How do you take the Laplace transform of e to the t plus 3? The answer is you don't, unless you know your pre-calculus, right? Or calculus. I mean, whoever you want to blame. If you haven't been taught this before, but I think you guys have seen this before. This is e to the 3 times e to the t. And as such, we get e to the minus 3s times e to the 3 times 1 over, s minus 1. And there you go. That's the Laplace transform of the exponential times the unit step function. Does that make sense? Yes, no, maybe so? Let's see here. So the theorem that we have is that the Laplace transform of f of t times the unit step function t minus a at s is equal to e to the minus, let's say, as times the Laplace transform of Where was I? F of t plus a, yeah. All right, so we could also say that f of t times u of t minus a is equal to the inverse Laplace transform, right, of e to the minus as times the Laplace transform of f of t plus a of s of t. And now we'll find out if I'm actually awake today or not. This next step gets me sometimes. Substitution is more difficult than it seems for some reason. If I let this thing here be, let's say, g of t, right? So I'm saying g of t is equal to f of t plus a, right? What is f of t then as it relates to g? T minus a? All right. So if I rewrite the theorem right there in terms of g rather than f, we'll find another law for the Laplace transform, one that we'll use. This one causes the students considerable suffering. But see, okay, so then notice that in this context, the Laplace transform of g of t is what we would call big G. Right? Big G is the Laplace transform of little g. And as such, the way I can read this is that g of t minus a, u of t minus a is equal to the inverse Laplace transform of e to the minus as times big G of s of t, right? But the way I usually, I mean, that's true. Actually, this is the way I usually use it. So there you go. Let's just put a box around it. Let me actually put this formula into practice, yeah? Suppose we want to solve a differential equation. It feels wrong not to have at least solve one differential equation today, right? So let's solve, make my life relatively easy. Example 8. Let us look at y prime prime plus y equal to the unit step function of t minus pi over 2 with, and then plus e to the t times the unit step function of t minus 1. There, I'll probably regret this. We're going to put y of 0 equal to y prime of 0 equals to 0 to make our life slightly easier. Let's see if we can hack our way through this problem. So the same thing we did last class. How do we solve things with the Laplace transform? We first of all take the Laplace transform. So the Laplace transform of this, we've got s squared